So what we're looking at here are some alternate activations for our substitution reactions. So these ones will all follow in quotes, and we'll see why in quotes, a bimolecular type mechanism. And it's a little bit weird to call it that because there's multiple steps within it, and the overall thing doesn't really fit the SN2 mechanism. But there's a critical stage in the formation of the product that's really pushing this bimolecular. And so when we're talking about it in that sense, really what we're referencing is looking at our reaction and noting that the type of reaction in all cases is some type of substitution, and figuring out which pattern it fits. Does it fit in SN1 or does it fit in SN2? Well, in the SN1, we get multiple products. In the SN2, we get one. Well, in each of these cases, we only get one product. Right? And so that's where we're saying it kind of fits the SN2 type mechanism. But we'll see in a second, or when we start to dig into these, that they don't exactly fit our standard default description of an SN2. And this would be a good thing for us that we're following this SN2 type in comparison to the last reaction set that we just looked at, because maybe you don't remember the last reaction set. Here's the last reaction set. So how are these reactions different from the new ones? And it's good because we already kind of addressed it. We get one product. And on top of it, we get very particular stereochemistry. So this stereochemistry thing is a tricky thing to do or note. And believe it or not, I entirely screwed up this video not more than 5 minutes ago and had to restart because I messed up the video. So let's call attention to some of those kind of critical points along the way. So first and foremost, we're seeing SOCl2 show up twice, but it comes out to two different conclusions. Either inversion of stereochemistry, which fits our standard SN2 dynamic, or retention, which doesn't fit our SN2 at all. And for those people being, oh, it must be SN1, it doesn't really fit SN1 either, because SN1 is stepwise in that substitution, and it's still a concerted mechanism. Okay? So we're not really fitting SN1 or SN2. The reagents are allowing some interesting mechanistic results to come out of it. And since we can't draw massive parallels out to other things, we haven't named those categories. We just kind of have to memorize it. This SOCl2 thing or differentiation really jumps into play based off of the solvent chosen. And some quick internet searching will show you that depending on your individual reference, they may choose to show it as a retention or as an inversion, and it's kind of wishy-washy all over the place. And that is problematic, so watch out for that. Be aware of that as a potential issue. I know for certain when I go through and grade that I'm going to be zeroing in on this exact aspect. If it just says SOCl2, you should be pushing retention of stereochemistry. If you see that PYR show up, do inversion. I'm not going to throw in another solvent. Okay? The other thing that's interesting to note on that is that we are seeing sulfur as an element, and that's not one of our common elements to work with. On top of which, if we look at the other reagents, we're seeing phosphorus showing up and this weird TS element showing up, which a quick look at the periodic table should tell you TS is not an element. Okay, so we're seeing some new pieces come into this. Just for reference, and we will address it, that TS is actually an abbreviation for the name of this large structure. Okay? TS is that piece, and it would usually connect out to some atom X. Right? Depending on the identity of that X, we would change the overall naming of our structure. But TS is in reference to toluene sulfonic or toluene sulfate. Okay? So that is that extra piece. So now what we have to do is look through our individual mechanisms, keeping in mind, why is the stereochemistry happening the way it should be happening? Okay? And remember, it is challenging. Like I said, I already goofed it in a previous recording. Okay? So if we continue on with this, we'll start with our thionyl chloride. So depending on those conditions, we can get kind of alternate chemistry happen. So the first thing that I'm going to go through and do is I'm going to ignore the presence of pyridine, because I think pyridine can potentially make it easier or more difficult depending on your perspective. Right? And so the next step we want to do is address just the reagents themselves. We could go through and look at the starting alcohol, but that's going to be a challenge because as we saw in the last video, that starting material has access to all the chemistries. And if it has access to all the chemistries, we don't really know which chemistry to do, which is why we should look at the thionyl chloride to see if that limits our choices. And if we go through and look at this, we should see that we have those halogens with lots of electrons. But as we learned in substitution, halogens don't act as particularly good nucleophiles. What they do act as is really good electron withdrawing groups, okay, or leaving groups. If they did that, that sulfur would start to become positive. Okay? Well, what happens with the oxygen? The oxygen with lone pair electrons, again, not particularly good as a nucleophile right off the bat. We have those electrons, but not particularly good, particularly if we consider that the chlorines are already withdrawing electrons from the sulfur. If anything, the oxygen wants to keep those electrons kind of in the structure to help stabilize that sulfur. Let's ignore the chlorines for the moment. If we look at the bonding patterns between the sulfur and the oxygen, we have this pi bond. We won't address the sigma bond. Why won't we address the sigma bond? Okay, so hopefully you acknowledge that the sigma bond is a stronger bond than the pi bond. Okay, so that pi bond, those electrons are likely also going to go towards the oxygen because the oxygen is more electronegative than the sulfur. Okay, so what we're now looking at is that we've got two conclusions saying that our thionyl chloride has a positive sulfur, which is indeed how it responds. Thionyl chloride acts as an electrophile, and a pretty darn good one at that, which then means all of those chemistries becomes nucleophile. So we would now go back and look at the structure of our alcohol and see that the lone pair electrons on our alcohol can now potentially come in and attack the sulfur. We have two potential arrows to go. We could break the chlorine, or we could break the pi bond to the oxygen. Technically, I already answered this question, but we're going to throw it at you again just to see how you're doing. We should be breaking the pi bond to the oxygen. And the reason being is that that is a weaker bond. So we'll go ahead and pop that off. Right? In that process, we now have the sulfur in the middle. We've got our oxygen now with 3 lone pair electrons. We still have our chlorines connected out here. And we would still have, or we would now have a positive oxygen from our starting alcohol because it's now lost a lone pair. That positive is not the greatest thing in the world, so we would like to somehow fix that. Okay? What picks that up is not critical to my perspective. Okay? So don't stress about that, but it is very likely that those electrons would go to our oxygen. Something's going to pick up that hydrogen with enough electronegativity or enough lone pair electrons that could stabilize that hydrogen better than the oxygen it was starting with. Okay? If we now look at our system, we still have that negative oxygen trailing on the outside. So we could have those electrons come in and we could kick out a chloride. The result, we now have that sulfur connected, our double bond to our oxygen, and we still have another chlorine out here. There are people that would suggest that since you just kicked out that chloride free floating around as a negative, and we have that H plus free floating around, that those two could hook up. It's not a bad thing to suggest in this case because those two things could come together to form HCl, which would not be soluble in the system, which would mean they would bubble off as a gas. Okay, so this is one of the reasons why we typically don't use this reagent in an undergraduate lab, because we produce hydrogen chloride gas as a byproduct, and that's not particularly safe. So now the next stage is what happens. Okay? What happens to our structure? Well, the whole point of this was to make a good leaving group. We needed this oxygen to somehow leave the structure. Well, if we go through and look, we have kind of stabilized that sulfur because it's missing a chlorine, but we put on an oxygen, and oxygen being more electronegative than chlorine, okay, isn't going to stabilize it all that well. So one of the things that could happen is the electrons from our oxygen could shuttle in. Okay? That's now going to make the oxygen happy, and it's going to exceed the electrons on our sulfur. But the sulfur can then eject the chlorines of our leaving group, or our chlorine electrons, and those can shuttle immediately back to our carbon. Okay. Why does this become important? And now we can connect our arrow all the way across. This may seem a bit crazy, but let's take a look at what happens. The end result is that we now have the chlorine connected. That chlorine didn't have time to go around to the back side of the structure, so it's now connected on the exact same side that the oxygen was located. So as far as stereochemistry goes, we have a retention. Note again, the structure shown here doesn't show that because it's tedious to show all those pieces. What else would we have floating around? Well, we would have formed sulfur dioxide, SO2. This is a second reason why we don't use thionyl chloride in an undergraduate lab, is sulfur dioxide is typically the compound they put, I think, into natural gas so that you know you have a gas leak. Okay? It stinks. Okay? It is a rotten egg, nasty gas smell. But since it is a gas, it bubbles out of the solution and it minimizes the reverse of this reaction. So we get a large progression towards our final reaction. So cool. We've now done our substitution, we've formed thionyl chloride, and since we've shown this all happening at once, we've also shown our mechanism in such a way that we get retention of stereochemistry, and that's pretty neat. Okay? I did address that there were some issues as far as the mechanism goes. If we think about this as an SN2, and we think back to what we learned in first semester, we should have seen this as one step. This is clearly not one step of a mechanism. If we go through and part this out, we have 1, 2, 3, 4 steps. What's going on here? Right? So if we look at where the substitution actually occurred, the substitution really didn't happen until the very end. And even then, it wasn't an SN2 because we got retention. Okay? But that's where the substitution reaction happened. Well, what happened in all of those other stages? Well, steps 1 through 3 had really only one purpose: make the leaving group better so that we can run the reaction. Remember, the alkyl has too many reactivities. So what happened at each of those individual stages? Let's take a look at step 1. In step 1, the electrons from our oxygen attacked the sulfur, causing the pi bond to break. Okay? Well, we broke a pi bond, so this has to be an addition. Right? What caused the pi bond to break? Well, this oxygen acting as a nucleophile. This was a nucleophile addition. The nucleophile addition is a reaction mechanism that we'll see in the next unit and we'll continue to elaborate on in subsequent reactions. Step 2, probably the easiest mechanism on here, so I'm going to put that in as a question. That is an acid-base reaction. All you've done is removed a hydrogen. In the next one, we're looking at the formation of a pi bond, so that must be an elimination. What did you eliminate, or what was eliminated from the structure in the course of this? We lost the chlorine. It was a nucleophile. So to run this reaction, we've actually done a nucleophilic addition, an acid base, a nucleophile elimination, and then the substitution reaction. All of those pieces are coming together to get the overall reaction. How do we know that these steps must be happening? That's where somebody's doing some hardcore analysis, 152 studying of rates and reaction concentrations. Some of this we can predict by looking at the individual pieces. Some of it you're just going to have to memorize, right? And so I leave you to decide which pattern you want to go through and fall through, okay? And so with all of that, remember, one of the things we started with is that we ignore the presence of pyridine. Okay, well, what happens with pyridine? Pyridine as a solvent is also a nucleophile. And that pyridine can react with our thionyl chloride first, giving us a free chloride. Okay? That free chloride is what's allowing for the backside attack. Okay? So the pyridine gets sterically hindered enough that we end up ejecting the leaving group and forming a chloride before we actually get the nucleophilic attack. Okay? So the result being is that the chloride can now come in and do a backside attack. So if we went through and looked at this overall reaction, what we're really saying is we have pyridine up here. Okay? Because you now have that free chloride can now come in and do the backside attack. As long as you've got time for that leaving group to exist and float around in solution, that's when you're going to get that backside attack. Okay? The leaving group is also much more sterically hindered. It limits and prevents some of that retention of stereochemistry. Okay? It is a little bit more of a complicated mechanism overall because it isn't quite as simple as what I'm showing here, but it's not far off. Okay? So this is what's neat. So based on the mechanism, we could get retention or inversion of stereochemistry. So why is thionyl chloride one of these cool reagents? So cool chemistry number one, any OH functionality, this reagent will work on. Okay? Thionyl chloride is so active as an electrophile that any alcohol or any OH, will react with this. Okay? And why balk at the statement of alcohol? Which of the following functional groups have OHs but are not alcohols? Okay, so that's kind of cool. That's going to become important when we move into our third unit and we look at carboxylic acid derivatives, because we need to get those carboxylic acids into other functional groups. We do that using thionyl chloride. Okay? Stereochemistry becomes much less important there because you maintain a carbonyl carbon there, so you don't have a stereocenter. And then step two that makes this cool is, depending on the presence of pyridine or not, you get retention of stereochemistry or you get inversion. So in the top case, should have been drawn a little bit better, and instead of having that chloride floating up there, we should have written that as PYR, which is our accepted notation for, or abbreviation for, pyridine. Okay, and in the bottom case, we get retention in stereochemistry without the presence of pyridine. Okay? So stereochemistry becomes a critical thing to watch out for, and we really have to be careful with this particular reagent. Okay? Again, this is taking a closer look at it. Pyridine, or PYR, has that nitrogen with that lone pair electron. We will talk about what that lone pair electron could potentially do in our very, very, very last unit. But the quick bottom line of that is that that lone pair cannot be delocalized through resonance. And since it can't go into resonance, the only place that that electron can go is outwards. Right? So it can act as a potential nucleophile. But due to the sterics, it is limited. So it is a sterically limited nucleophile. And that's why it can act as a really good solvent, because it's not going to run as a nucleophile very often. So that lone pair on the nitrogen can go through and react, and we go through and form our kind of sulfur ester. That chloride can now come in and do a backside attack. We still form our thionyl chloride, and we would reform the pyridine. So it kind of acts as a catalyst. This does address kind of an issue here at the bottom. I have seen questions written both directions, okay, where you just have, let's say, a reagent. Let's draw one real quickly here if my computer catches up with me. So if we had a particular reagent, come on. If we had a reagent with a stereocenter and it just said SOCl2, what should you do? Should you do inversion or should you do retention? Unfortunately, again, I've seen questions go both ways. So be very careful with this. When you look at a question, you need to look for that pyridine. If you see the pyridine or PYR, you should be doing inversion. If you do not see that solvent, you should be doing retention, and just leave it at that. Okay? I am very cognizant of this issue, and so whenever I have a test question, I'm going to watch for that. But I can't guarantee, say, standardized tests will have that same kind of awareness with the particular reagent. Like I said, you take a quick search on the internet, you're going to see mechanisms going both ways without referencing the solvent. So be careful. Okay, and then there we go. Without the pyridine, we get retention. Okay? Which gets us to our phosphorus activation. When we talked about it, or we put it up on the quick summary slide, the summary slides showed it as PBr or PX3. It can really be any halogen, but it is most commonly done with bromides. And when we go through and look, oh man, the connectivity is having some big problems. When we again go through and address the reactivity of our phosphorus, we may see that lone pair of electrons and be like, oh, it must act as a nucleophile. But you also have to consider that you have these 3 bromines on the outside. Those bromines being electronegative are all withdrawing electron density, which effectively nullifies the activity of that phosphorus lone pair in this case, which means that phosphorus ends up acting as an electrophile. Why is that useful? Well, now our oxygen can come in and attack, very similar to the sulfur mechanism, right? And we can end up forming a good leaving group with our PBRs out here. We get Br minus floating around. Whoops. Br minus floating around is a nice stable structure, and because it is stable, it can exist for long enough to come in and do a backside attack. That backside attack, man, that looks sloppy, let's fix that. That backside attack is what's going to now get us that inversion in the mechanism. Because again, we've been talking about mechanisms. Let's go through and break down the mechanistic pieces behind this one in an attempt to show the inversion. I know that is a horrible way to draw that. Please don't yell at me for that too much. We're really seeing the SN2 happening at the end there. We're getting the clear backside attack with the ejection of our leaving group. That very first step we aren't used to seeing with an SN2, and that's because it's not an SN2, right? In this case, that very first step that we're seeing is also an SN2, right? We're doing, and it's not obvious here, but we're breaking and forming a nucleophile bond and a leaving group bond all at the exact same instant. So the phosphorus activation is actually a back-to-back SN2 mechanism, and it is that process that is really getting us our inversion in stereochemistry. The other thing that's cool with this particular reagent is just like thionyl chloride, it will react with all alcohol functional groups, okay? All OHs, which means alcohol and our carboxylic acids, as we previously talked about, okay? So there we go, our nice little process. Which gets us to the last one in this particular lecture video. We're looking at our tosylate. That TS, as we talked about already, is referencing what is known as toluene sulfonic or toluene sulfate. Okay? And that's that structure that we're looking at there. Oh, cool, it connected faster this time. This piece is our toluene. This piece is effectively our sulfate. Right? What I want you to do is look for patterns, because if you can find those patterns, that can help you predict something of the reactivity. So if we were to go through and say, reference that squiggle that I just erased, okay, and we made that an OH, right? What does that species act similarly to? Well, if we can recognize patterns behind this, what we're really seeing is we have a sulfur, we have 3 oxygens, and a hydrogen, and then we have some X group extra. Okay? If we made that X group extra an OH, what do we have? We would have H2SO4 or sulfuric acid. Okay? When we put an OH on there, that hydrogen becomes exceptionally acidic, very similar to sulfuric acid. Why does it become acidic? Resonance stabilization of the lone pairs through that massive pi system. So why would I choose to use toluene sulfonic acid over sulfuric acid? Well, sulfuric acid is very, very polar, and so is largely only soluble in, water. Whereas toluene sulfonic acid has roughly the same acidic characteristics, but also has that non-polar tail. which now increases the solubility of this acid in organic materials, say for an organic chemistry class, and that ups the utility of our toluene sulfonic acid. Okay? What happens if instead of that squiggle being, an OH, we made it a chloride? Okay, well, what does that now do to the chemistry? Okay, well, the chloride being electronegative withdraws electrons. Really what ends up happening is we make that sulfur exceptionally positive, which means electrophile. Right? If it's an electrophile, what can now happen? The electrons from our alcohol can go through an attack, and we run a similar mechanism to our sterically hindered thionyl chloride. Right? And so that's the chemistry behind that. So again, if you're looking for those patterns, you can try and find ways to simplify the amount of work that you have to go through and to memorize these reagents. If you aren't looking for those patterns, then you really just have to memorize everything. Good luck. Okay. And with that, I believe I'm done. Let's go ahead and check real quickly. Yep. So thanks for listening. We'll go ahead and move on into our ethers and epoxides in the next video. And let's make sure we stop it this time.